Okay, looking at the following domino results that we got from the vernier interface. That's the device that I was interacting with in class that seemed to keep resetting itself every time I set it up. So that device has a screen, and the screen reads time and here and voltage here. And as you know, we released the domino, breaking a circuit. The domino fell on something else and completed the circuit so that the voltage was up here until we released the domino, at which point the voltage fell straight down to 0, stayed there while the domino fell, and then came back to the original voltage after the domino, at the instant the domino hit the table. Now, all this isn't quite instantaneous, but this is all done by the build-up and collapse of electric fields, which occurs very, very quickly in very tiny increments of seconds. So there's essentially no uncertainty involved with that aspect of the observation. I'll also mention we were taking 1,000 readings per second, so that whatever time we measure could be off by 1 or 2 thousandths of a second. That's entirely possible. Depending on where the readings, was there a reading at the very instant I released it? Well, I doubt it. Somewhere a little bit after the instant I released it. Was there a reading at the instant the domino hit? No, there would have been a reading sometime within 1,000th of a second after. Now, the dimensions here. On the screen we had 1.5 seconds between here and here. And that was just a readout on the screen, it showed us that. And I took a meter stick and I measured the distance from here to here. It's 66 millimeters. And I also measured the distance from here to here. And that turned out to be 6 millimeters. If you got a decent sized screen, you can probably read that okay, but it's 6 millimeters. Okay, so the question is, how much time does that correspond to? Okay, this can be answered by proportionality, it can be answered by rates, so it's a good illustration, so let's see how we might work it out. First of all, if we do it by proportionality, let's let y be distance, matter of fact, let's let x be distance and t be time. Now what we're trying to find is time. What we've measured is distance, and for that reason I'm going to set up the proportionality this way. X equals, and I just did exactly what I said I wasn't going to do. T equals kx. Okay, now why would distance and time be proportional to one another? Well, for every millimeter along here, there's a certain amount of time, and it's the same time for every millimeter, because we have a consistent scale along the bottom of the graph. The program that runs the interface makes it so. Okay, so the time between 2 points is proportional to the distance between 2 points. And let's make it real clear that x is the distance between the points, t is the time between the points. We could even call that a delta x and a delta t, but that might end up being confusing. So we want to evaluate our proportionality constant k. Well, t equals 1.5 seconds when x equals 66 millimeters. So 1.5 seconds equals k times 66 millimeters. So that k is 1.5 seconds divided by 66 millimeters, as we get by the fundamental operation of dividing both sides by 66 millimeters in this case, or multiplying both sides by the reciprocal or the multiplicative inverse of 66 millimeters. It's a reciprocal, it's a multiplicative inverse. Okay, so we divide that, and what do we get? Well, 2 times 66 is 132, leaves 18 up to 150. 18 over 66 is more than 1/3, less than 1/4. So I'm going to say that's approximately 0.023 seconds per millimeter. Now you can check my calculation. We'll see if it works out. I did that quickly in my head and I haven't really double checked it. So anyhow, that's what we have, and we're going to use that, and you can refine that as you wish. Now I will comment that the 6 millimeters was not an exact measurement. In the first place, I wasn't even wearing my glasses, although I was a decent distance away, I could see it pretty clearly. I think it was maybe a little less than 6 millimeters, but certainly closer to 6 than 5. So there's some uncertainty excuse me, in this measurement. Okay, so, but based on that measurement, this is what we get approximately for the value of K. So T is 0.023 seconds per millimeter times X. So if X equals 66 or 6 millimeters, then T, the time between those readings, is 0.023 seconds per millimeter times 6 millimeters. And that comes out 0.138 seconds. Now, I wasn't fudging. I think that's actually one of the estimates I've already put down on the website, but that's where that comes from. Okay. Now, the other way of seeing this is just that 0.023 seconds per millimeter is a rate. It's the rate of change of the time represented by this graph with respect to distance. So it's kind of an interesting connection that you might want to ponder just a little bit.